Okay, hello. I'm making this video to give an overview of the feasibility aspects of photonic insecticides or laser drones. Right, you can see here a drone, and it basically shoots insects. Uh, so let's. This is a bit of a moonshot idea. So let's go over the aspects individually and see if it is feasible or not. So to be able to make this work, we need to first be able to find the target insect, in this case Colorado beetle. We need to be able to find it. Then we need to be able to, it needs to be eye safe, right? It's a laser, so it should be safe for its surroundings. Then we need to be able to track and aim on the beetle. Um, it needs to be economical, so it doesn't need to be cheaper than conventional pesticides because it's a biological solution, but ideally it's better and more effective than current biological solutions. Then we are going to compare it to why a drone is likely more cost effective than anything that is driving on the ground. And we will also, part of this, like the cost per hectare and things like that, depends on a full simulation. So let's get into the first aspect. We need to be able to find them. And for this, we can basically open the correct section. Here, can we find them? And or maybe the best way is to just look first. We have some drone footage where you can see the actual insect, so we can get an actual look on reality. So this is just shot with the DJI Mini on a potato field, and here you can see I have you can see the target insects. These are the larvae, and I ran a very simple, super simple algorithm. You cannot even call it an AI algorithm. It's just thresholds on this specific type of pink, and you can see how the insect is sitting on top of the plants and how it's very visible and very easy to find with AI. So you can see here, you can see them all. So here is a cluster, and they also appear, this is interesting, in clusters. So I also have videos where I walk in the fields and I take with my phone sideways camera footage, so you can see that indeed 90% of this insect is sitting in a region that is reachable by the sunlight, because they like the heat. It helps them develop because they're cold-blooded. This is a typical cluster, what you see here. This will be a typical cluster. So one adult laid some eggs here, and they all hatched. And now here you have all the little the larvae. Right, and then I think also going a bit back here, here you can see an adult. So this is the adult. They are also mostly on top, and you can see they're very easy to see. So this was actual camera footage. I'm not gonna go through it because the idea of this video is just to give a broad overview. So now there are also commercial solutions that can build you pest maps. So they basically take from higher altitudes, they take photos with drone like this, and then they look specifically for the Colorado beetle. So you can see it here. It's one of the things that they detect, and basically it just comes down to the resolution of your camera. So then if you have a high resolution camera, you can fly quite high and you can identify the individual insects. And to do that, we know here I put an example image of so this is a Colorado beetle on some background, some leaves in the field, and so area per photo. So basically would be if the drone flies higher. Here you can see the drones flying. If they fly higher, then you need less, right? To get the required ground sampling level. So we need about 0.8 millimeters per pixel. So we can slide up to, we have about this, and this is then what your photo looks like, right? So up to this level is kind of the limit when you can separate the beetle from a piece of background. It's on the limit. Now if you get a high resolution camera, so this now presumes a camera of 48 megapixels, but like the Mavic 4, which costs around 2.3k, has a 100 megapixel camera. So then this becomes here. So now you can see it's very clear again. So now I can basically fly higher. So I can capture more. You can see the dots here in the simulation get wider. So let me put it to this. Okay, and then let me just put, well, the amount of drones that are doing this makes no difference, I think, in the cost. So you can see a drone flying from one point to another point, capturing this specific area with this resolution, and this is what it will see. And then you can run AI on this, and then if you just do the calculation of 1 flight hour of the drone, you get a number, right? So this is 10 euros or 11 euros per hectare per season. So this is every day it would fly over this, and that's the cost. And then if the drone is faster, then the cost should go down. But maybe that's a more expensive drone, or it has more wear. I'm not sure of that, but so here you can see now we have a drone that has a higher acceleration, so it can go faster from one point to the other point. So, but anyway, these numbers look, within reason, right? So they're in reason. If you have a bigger field, just add some drones and it will go in parallel. Also here we have a commercial solution, Tective, which keeps drones in the air, which has fully autonomous drones. So this is their drone station. They focus mostly on military applications, but they're also doing trials in the Netherlands where these drones are flying fully autonomous over potato fields with all regulatory requirements met. So this is already in progress, and then the drone lands in here. This is its docking station. It recharges and it goes back to its mission. So this already exists. So this can we find them? So we can. I think I've shown that we can, and at a reasonable price. Then we have eye safety, which is something that people are very concerned about, for good reason, of course, but actually is reasonable to solve, because the University of Brussels actually, as part of the study related to this project, in which they concluded that you can make it eye safe and economical, but especially eye safe, and the optical system can be made. So here you can see around 1500 nanometers. This isn't the intended wavelength to be used, because it cannot penetrate into the eye up to the retina. So the worst damage it can do is damage the front of your eye, which is repairable by surgery. It's of course not ideal, but it's much better than damaging the retina. Then you're permanently blind. So this cannot permanently blind you. That's a big advantage. And you can see it absorbs this wavelength around the head, around 25%. And so from this we can calculate that if we model, unfortunately there is no yet empirical tests, but there are tests on other kinds of beetles that kind of confirm this. So if you model the head as 1 cubic millimeter, just simple, of water, then we know it will absorb 25% of the energy that we shine at it. Then we can calculate how fast this cubic millimeter of water will get to a temperature where the proteins denature, which is around 60 degrees normally. So basically like cooking an egg, it goes from transparent to white. That's the protein denaturing. So, and no insect survived. So if you just target a head and you model it as a small cubic of millimeter, then you know how much energy you need, and then you can discuss, but let's say it's between 0.5 to 3 joules. And then also this shows actually that this amount of energy is negligible. that has no effect on the battery actually. In comparison to flying, this is nothing. But now we know this. Okay, now the question is, how do you deliver this energy in a safe way? Well, the way you do it is you have a the way you do it is we will start from you use a big optic basically. So here you start from a beam that is wide, then it gets focused down to a point, and because of this, after the point it diverges again. This means very quickly it becomes the energy per unit of surface area becomes smaller than the energy that would be required to damage a human eye. There are standards of this, which the University of Brussels has looked up and calculated, and this is just a simple calculator. So then the nominal safety zone is basically this distance, the distance you need to be away from the drone. You should not be there because there it can injure your eye. If in the theoretical case that the laser would be pointed at your eye, which is it's never going to be. But okay, so then here we can put a practical starting diameter of the beam, which you can find here. Are the MEMS mirrors. I believe they go up to 1 centimeter possible. So they can put mirrors on this. Yeah. So here you have the MEMS mirror. So we start from a beam that is 7.5 millimeters wide, and then if you make this focal point closer to the drone, then it diverges quickly after that. So then your nominal safety zone gets smaller, but maybe practical working distance is like 1 meter. That means the human needs to be away 3 meters. So basically, you shouldn't shoot if there is a human detected between 3 meters, which is very easy to detect with modern cameras, right? And so basically, the drone just monitors its surrounding. If I have some kind of animation for it, but like this. So if there is no human, then fine. If within 3 meters there is a human detected with a rotating camera or anything like that, then you don't fire. But even then, if there would be a human here, I mean, the drone is firing downwards. It's never allowed to fire in a horizontal fashion, and it only can fire at the actual beetle. So 300, let's say 250 times per second, it will be checking that what it's seeing, what it's aimed at, is the actual beetle. And if it's not a beetle, then it will not fire. So, I mean, even if you're inside the safety zone, in reality, it will not harm you. So it's more of a theoretical case. And said, if it would harm your eye, it is not going to cause permanent damage. There is a good chance it heals by itself, and worst case, you need surgery. Which is less dangerous than, for example, autonomous driving cars. If they hit you, then you can be dead, or you're mangled, your bones, crushed to pieces and stuff. So this is definitely not like a more unsafe technology than self-driving cars. So we can find them. We don't have this one. Well, we can find them cheaply. We can do it eye safe. Also, the laser beam does not consume a lot of energy for the battery. Then can we track them? There the answer is also very likely yes. Because the whole, how it actually works, this is the optical system, I mean, very broadly, roughly. So you have a zoomed in camera, you have a laser source. We basically optically align a camera with a laser. And so now they have one optical path. Here is the MEMS mirror. So now the camera is looking at this. Now the camera is looking at this. So basically we steer the MEMS mirror so it's looking exactly at the target. And then we know whatever is in the center of what this camera is seeing, that's where the laser is. So this basically removes depth, which makes targeting easy. And this design, or slight variations of it, but exactly this has been actually tested also. You can see it in action here in a foveated camera. This is called. And let's skip the. I was gonna do it on the website itself because I have some camera. I've integrated it here. So So this is a prototype of a foveated camera. So here it's a big thing. Um, so yeah, so you can see, so basically we see a beetle here. Then we will rotate the MEMS mirror as they're doing now and bring this zoomed in, more detailed view towards it, and then we put it exactly, we put the center of the field of view of this camera exactly on the target, for example the head of the beetle, and then we engage the laser. Right, so that's what they're doing here. Of course, but they don't have the laser. They only have, they select the region of interest with the camera, but adding a laser there changes nothing. It's exactly the same method of operation. And here you can see them, how basically what you get is, let's call this aiming while you're on a shaky platform. So they will, here they are, this detail view, the MEMS mirror, they are keeping it, tracking this tower. And so you can imagine that this is the beetle, and we're just keeping the laser on there. So this is a very shaky platform. This is now a human that's doing this shaking. This is a car that's doing the shaking, and we are stabilizing on this image. So this is basically how it works, and we can also model this loop in a simulation, which I have done, and then you get an outcome which is very positive. Also, a drone has both a high frequency vibration and low frequency vibration. The high frequency vibration is caused by the propellers, right? And it's, yeah, anywhere from 50 hertz and up. But the good thing is, high frequency vibration you can very easily filter out. Just use some rubber pads, and the high frequency vibrations are filtered out. This is why they use rubber pads as camera stabilizers or vibration isolation on a drone. The low frequency vibration, so that's just the drone going a little bit to the left in a centimeter and coming back to the center and to the right and things like that. Well, this is a low frequency, so for this fast loop, it's like standing still, because this loop we can make it at least 250 times per second. So here I've put basically how fast the camera is, how many frames per second, and then you need to have very fast processing, which you can also do, which is in an FPGA chip. So you use a hardware optimized chip. So basically run not a neural net probably, but feature tracking on a specialized chip that's very fast. And then here you can set how much the drone would be vibrating, and this is the simulation. So this actually runs. Here you can see the running of the take a picture, look where is the head of the beetle, then adapt, once you found the head of the beetle, adapt the MEMS mirror, and so that that we're looking again straight on the head of the beetle, and do that many times per second. So here I can look at it in slow motion, and you can actually see the steps go. So it's look where the head is, find the head, so look just with the camera, expose the camera, right? Then find the head. This is the FPGA chip running. Then you give the appropriate command via a PID controller to a mirror, the MEMS mirror. The mirror adjusts, and this puts the beetle head exactly in the center point of the viewpoint again. So we can maybe see it a bit more if we have some more shakiness. And then we can also model here the water content of the head. We know the amount of energy being delivered, so we know approximately, we can estimate how fast this will be rising in temperature. And so it starts from, let's say, 22 degrees, and then we go to, let's say, 50 degrees, and then the beetle is dead. So you can see this, and here you have the milliseconds that are being tracked. So if we add more power, we will reach it faster. So this is taking now actually quite long, 500 milliseconds. We're gonna have maybe a second or so to kill the beetle. That is a long time, but there is no I don't know how much I should have put here, a way to regulate the optical wattage that is being used. Maybe I say it here. Um, Maybe I'm using the optical wattage that is down below. I'm not sure, but you can. There is no. So this is an X beetle. We can put a lot of optical wattage. That's no problem. So let me show you also that. So we can do it very lightweight. So this is a diode. I believe this is a. This is 1 watt. You can also get them in 5 watts. This is a driver for this kind of diode of 1500 nanometers. Basically, a rule of thumb is 1 watt of optical power is 40 grams. So yeah, so this is quite low weight. And then here is just to I built actually. I mounted a laser of 50 optical power watts on a drone and had it fire, just to show that this is not actually any. This is not actually a blocking concept. Okay, so maybe it's on the other page. This project is not yet perfect. There are, little things like this. This is the flying prototype actually, where you have a 50-watt laser on a drone in flight. So built by an amateur. So this is completely possible. And firing. So you can see it shoot here. So this is not a problem, and 50 watts, that this also kills the beetle for sure. Yeah, so this is not a problem. So we can put as many optical power as we want, and then you can say, well, will this not make it less safe for the human? And the answer is yes. More optical power makes it less safe, but again, we can mitigate this by here you can actually set the optical power. So it's 10 watts if we add more optical power. And okay, in this calculation, it's just going to reduce the exposure time, so that's why it's not updating the nominal safety zone. But basically, you use a bigger optic, or you stay closer to you reduce the focal point. So there is a lot of engineering degrees of freedom that you can find a good balance between these. Yes, so that's this. Then, what else do we have? I might, after this talk, do just a little bit of this as a slider, so I can set the optical power here. So we can make it eye safe, we can find them, we can track the beetle based on the Fovea Cam prototype. Then we get to the question, yes, but will this be economically feasible, right? How many energy is this using? And the main cost driver is of course the battery of the drone, which always battery only has between 500 to 1,000 cycles that you can charge it, and then it's useless. You need to buy a new battery. But this is something you can model. So what I basically did to, if you want to, actually almost everything about these questions you can model. Alright, so and that's what I did. So you can answer these questions by modeling them. So here I modeled with the help of Claude, which is okay, right? This is like a game. It's very good in doing physics simulations. So here you can see, I'm gonna put it on potato. Here you can see the drone flying with it starts with 100% full battery, and it just is gonna visit every location of every target insect. So here you have a virtual field, and you can put any distribution of insects that you want. You can simulate the detectability of insects. You can then simulate flying there where the drone is. We're doing here, and we just model the physics and energy requirements. The energy that this virtual drone is using to move to locations and stuff is very close to actual observed telemetry from actual drones. So there is an open data set which I described here, but basically it's within 10% of an actual drone. So here you can put in the weight and things like that of your drone, and if you put in the parameters of the captured data set, then we get within 10% accuracy. So the model is quite close to reality, and you can see it moves in a way that is quite close to reality. So obviously no number of a simulation is going to be exact, but doesn't have to be. It just gives an order of magnitude. And so now we can run this simulation. Also, this drone, its battery will get depleted, then it will fly back to its recharge station, beat it a bit, and then go continue its mission. Right, so you can make this as detailed as you want. And this is how you can calculate cost per hectare then, because we know how much energy this is consuming, and then we can we know the distribution of beetles, and then you can look how much beetles it can kill per unit of time, type, and how many times it needs to recharge. So you can calculate your required recharge cycles, and so that this allows you, and standard drone maintenance and things like that. So this allows you to completely model the cost per hectare. The most unknown, so what I've done also is I've used Poisson distribution to model the beetle distribution. I haven't clustered them. In reality, they are clustered, which makes it easier for the drone, right? Because it doesn't need to go to the next location as many times. It can kind of stay in one location. So the more that the beetles are in one clustered, the easier, the less energy it takes. So and basically now you can then do a parameter sweep for different pest pressures of a field, and then you have your cost per hectare for pest pressure, which I have done here. So this is just the results of this physics simulation of a drone flying. Oh no, this is actually modeling one drone hour. So here I've modeled. So here you can put. Here you have one sweep, and then you have seasonal. It's more interesting to look at seasonal. You have the cost of your depreciation of your airframe, laser, battery, electricity, scouting. You can again model this as much as you want. Here we have a kind of simplified view of the beetle distribution on a field with a Poisson distribution. So you can see the beetles come from one side of the field, because this is normally the neighboring field, and then they distribute kind of like that. And then you can see how much this would cost per hectare, and we have here also, this is so by manipulating a slider we can see the cost per hectare that comes from the simulation based on physics simulation of the drone, which is very close to reality as seen in empirical data. And so we can see that for almost all pest distributions, but basically for all pest distributions, we are below the 300 euros per hectare, which is a baseline cost for like biological control, nematodes. And for the low pest pressure, we are below the 50 to 70 cost per hectares for standard chemicals for spraying. If we only use battery, if we don't have depreciation, so you can see it's very sensitive to the cost of the actual drone, which would come down a lot over time possibly. And another trick we can do just one layer of the neonicotinoid, a kind of chemical that they're trying to phase out the European Union because it's killing the bees. But right now they're spraying the whole field, and this, or like applying it to the roots of the potatoes. If we just do one border, this stops most of the beetles, and this reduces the amount of work that the drone needs to do dramatically. So then we can basically go below standard chemical solution in a, let's call it 90% biological solution versus 100% chemical solution. Then we have, let's go back to the overview. So we can do it, cost effective. Then why fly? Why not drive? This is a question that always comes back. Well, the answer there lies in the fact I modeled it. And if you would start to drive, well, either you go with a standard tractor and a big laser weeder and stuff, something like carbon robotics, something like this. But these machines, they cost around €1 million or something, and you need to you pull them with a tractor which has maintenance, fuel, things like that. And if you model all those things, then you end up with a cost that is something like this. So you have one operator or zero, and you get something like this. Just in terms of fuel, consumables, things like that, depreciation. This is no, so a lot more. So something like this. 1.2 million is a reasonable price. I'm not speaking for this company, of course, but these are realistic prices. So then, okay, let's not go with that. Let's go with something super tuned down cord, something like this, something very lightweight, solar panel. This is what Pantix laser fry automatic cord does. And then we can see, so let's model this. So basically we put machine price, something very cheap, 20,000. Working with, this is about 2 meters. Let's say 3. My drone is constant, but okay, 3. Working speed is, let's put a reasonable 5 kilometers an hour, fully automated. And let's get rid of the fuel and tractor costs and things like that. And then we get to about this comparison. So probably the drone can still beat it in terms of price, but if you start to look for commercial footage of this robot, this drone in operation, then you don't find any. And the reason is very likely because I don't want to speak for them again, but likely it just doesn't work. Because this is a small little vehicle, so if it's rainy, its tracks, it will get stuck. Then if the plants are grown like this is a realistic field, so it cannot get through, or it's going to damage the plants. If you damage their leaves and cut off branches, then you actually create fungal infections and stuff like that. So the fact that this is not a commercial solution, I cannot find anything of it, says some things about it. And then it's probably still a lot more expensive, and also it's not adaptable to different situations. So the drone, it really goes everywhere. It goes, this is rice, this is yellow stem borer, eggs of the yellow stem borer, the main pest of rice of half of the world. So it puts its eggs on the tip of the rice leaf. So for the drone this works. It doesn't work for a cart, orchards, all kinds of the drone goes everywhere, right? Greenhouses, things like that. In general, we can just say that all things considered, right, the cheapest way to do something is usually the smallest machine that can do it, right? And also, here I only did like three passes per season, but in reality, the drone is constant, so it's like 30. So then you get. So this gives an idea why a drone and not a cart. It all comes down to the weight of the optical unit, which I hope we can get down like around 200 grams, 300 grams, something like that. And then flying is just faster. So that's that. And then what else did I model? Potato leaves don't burn. If you poke holes in potato leaves and lots of other plants, they don't really care. You can remove up to 10% of the leaf surface of the plant. Then, because the drone is quite small, if the optical unit is small, lightweight, and the drone is small, I'm hoping for a drone of 1.5 kilo, something like that. That means it's much easier to regulate actually for autonomous flights, because a drone of 1.5 kilos, if it flies against a human or a car, it doesn't really do any damage. This is very different than a spray drone that is dragging like 30 kilograms up in the air. That will just decapitate you. So but here you can probably put your finger in the propeller and it's going to be fine. It's like a DJI Mini drone. And then we have some regulation costs. Somebody referred to that, so I modeled it. Which just, so you need some license and stuff like that, but that just goes down per hectares. You can play around with it. this kind of stuff. And then I have some more de-risking videos, which let's quickly go over it. So here we have a laser beam on a drone that is being stabilized by a MEMS mirror. Like this is the drone. This one. So here is yeah, it's stabilized. So MEMS mirror is stabilized. So removing the low vibration frequencies of the drone. Tracking, I went over this. So we have very high powerful laser on a drone. This is this same high power laser killing a beetle. The fact that we can, if you want to, we can make a lot of drones. It's not really a problem. And then I have some possibly other de-risking videos. Let me see, that are just interesting. Here you have the video of sideway view and like the distribution of beetles on a field. Here you have the fact that this optical unit is very lightweight, even though it's 50 optical watts. Tracking beetles on cheap hardware. Let's see, you can see them being tracked even if they're out of focus and things like that. Okay, and this is hopeful experimentation. This is visualizing insects under event cameras, which can run at 1000 frames per second. So this would allow a drone to fly over a field at 50 kilometers an hour and see all the insects. Possibly, this is one pathway. This is that the larvae, they die from a 5-watt laser, so it's very easy to build. And those are the main things.